There we go. All right. So we're grading exam 1 now. We're using a new software to grade exams, which is actually pretty cool, but there's a lot more setup than I thought there was. So I've been scanning and rescanning your exams, and some of you write very illegibly. So we'll work around it, but it's taking a little longer than I'd hoped. I hope that on Monday we'll be able to return the exams. I can't tell you, I don't exactly know how the exams get returned. I don't believe you get a physical copy back, but I think you'll be able to download a scanned copy with comments and the grade through Icon. At least I think that's the way Gradescope works. Question day 6 is released today after class, due Monday, usual thing. Homework 1 will be coming soon, and that'll be something you do individually with about a 2-week window. We're getting to some of the good stuff now that we're done with the basics, so we'll have a little bit more capability in our coding, and we'll be able to take on a little bit more complicated problems than the questions of the day in the labs. I keep getting notes saying, you haven't regraded lab 2. These regrades take a huge amount of time for, especially questions of the day in labs for like 1 or 2 points. I have to manually find your file, manually load it into Python, sometimes correct indentation errors. It's a fairly low priority, so I have gotten your notes. I will get to it as soon as I can, and then I will run a whole batch of them when I get a chance to. But it's a much lower priority than grading the exams graded, and I hope you understand that. Okay, so where were we? Well, before the exam, we were talking about sequence functions. And by the way, what did you think of the exam? Was it hard? How many thought it was really hard? A few. How many thought it was kind of hard? Was the difficulty limited to 1 or 2 problems? So who thought problem 1 was the hardest? Everybody should have seen, that was a lab problem. You should have seen that one coming. Problem 2, was that hard for you, the individual evaluations? It's tedious, right? That's tedious. I don't think it's hard. I think you have to really sit there and parse it out. First part of problem 3. How many thought that was hard? Okay. And second part of problem 3? Lordy, that was a stinker. That's a cool problem. You're going to hate it when you see the solution. But it's a learning experience. Okay, so that made me think of this slide, made me think of that problem because at the core of that problem is a mapping issue, right? So you want to map. So we've talked about sequences and sequence functions, max, min, sum, all, any. Also map, which is not on here but should be. And today we're going to start talking about other types of ways of getting work done other than functions. So all we've seen so far are functions, but Python also has these things called objects. And you've probably heard the term object-oriented languages. You know Java's object-oriented, and you know C++ is object-oriented. And C isn't, and Lisp isn't, and Scheme isn't, and it's almost like a badge of honor. I'm object-oriented, you're not. It's not like that at all. Python is not strictly object-oriented. In some languages, so languages come in generations, right? At the beginning, we had machine language. Every time you bought a new machine, you had to rewrite all your code. Then we had sort of first-generation languages. Think COBOL, Fortran, and various generations of languages. You eventually get to languages that are imperative languages like Fortran, COBOL, and C. You get to sort of functional languages like Lisp. Eventually, in 1980, a language called Smalltalk was created that was object-oriented. So we've gotten through C, Pascal, ALGOL, all these other languages. You get to Smalltalk 80, which was this kind of interesting take on how languages should be constructed, where everything was an object. You didn't compute by calling functions. You computed by having one object send a message to the other object. Something along the lines of add me. And this object would say, oh, okay, I'll add you. And you would add those two things together, and you get a new object back. It's kind of crazy, actually, but the presence of objects was meant to make software easier to modify and maintain. And object-oriented quickly became kind of a fad. I went through an object-oriented zealot phase as an undergraduate. Everything was an object. I did everything in the object-oriented sense. But like all things, there's too much of that sometimes, and these things get scaled back. Later, I went through this crazy functional stage where everything was a function. We all go through these different sort of philosophical bents on how you structure your code. Python, to its credit, is agnostic about this. It supports all of these things. Sure, there are objects. There's also functions. And I'm teaching you to write Python in a very functional sort of way. So you can be imperative, you can be functional, you can be object-oriented. Python is all things to all people. Now, you've seen some of these already. Not many, but you've seen that we have some things that get added to sequences, say. Sequences like range. You know, these are objects inside Python. Lists are objects. Strings are objects. Tuples are objects. Dictionaries and sets are objects. Integers are not. Floating point numbers are not. But those things that are objects, like ranges, have a whole slew of really, they're like functions that get invoked with this funny dot notation. So this particular function says, I have a range from 1 to 100 by 3. So that's 1, 4, 7, 10, 13, and so on. I want to know what the 52nd element of that, I want to know the index of where 52 is in that range. And so this method, it's called a method, says, I'm going to look for 52 in this range, and I'm going to return the position of 52. It's the 17th, starting from 0, 17th index. So in other words, range 1, 103, square bracket 17, right square bracket is going to be 52. I just said that. How about this? This is a test. It's a string. It's an object. It has a method called upper, which returns a new string that upcases everything in that string. So everything becomes uppercase. As you might expect, there's another function that does the lowercase, and another function that does title case, and so on. There's all sorts of methods. I shouldn't say function. All sorts of methods that manipulate the string. One of the cool things about, and so you should notice two things. First of all, the method itself is appended to the end of the string with a dot notation. We'll talk about this in a minute. And the method itself also takes arguments, just like a function. So the method really is a function attached to an object. One of the cool things about dot notation is I can string together things I want to do to that object so they get done in sequence. There's a language that makes a whole sort of philosophy out of stringing together dotted notations. Some of you may have written some of that language. But in Python, it is also a thing. I don't think it's particularly readable, but what this says is convert the string to uppercase, that looks like this, and then apply the split method. Now, the split method on strings actually takes the string, and depending on the argument, which here is there is no argument, methods often have multiple optional arguments. There are no arguments provided here, no values provided here. It will, by default, take that string and split it on whitespace characters, returning a list of strings that are words in that original space-separated sequences of string characters in the original string. So we've seen before, briefly, the opposite of split, which is join, which takes something very much like this and joins it back together into a string. So we have split and join as sort of inverses of each other with appropriate arguments. Well, here's a tuple with an index scheme just like range, exactly the same thing. It's a 3. So one of the things you notice here is that some of the methods apply to more than one object. This is one of the pluses of object-oriented programming, is that methods are often shared among objects. So here we have a tuple, here we have a range. I bet that a string also has an index argument, an index method does. All of these sequence types share, just like they share some functions on sequence types, they also share methods on those sequence types. Not all of them, but a good number of them. So a few lectures ago, I had a list of priorities, sort of the precedence of operations in Python. And you may remember that functions are the highest precedence followed by indexing, and then third, method invocation. So methods are really like functions attached to objects, but functions takes precedence in the order of operations. And indexing a sequence takes precedence over methods in order of operations. So keep that in mind. This is the way, if I give you another one of those long strings to evaluate, you need to know which thing happens first. And this is what resolves that ambiguity. So they're like functions, but they're attached with that dot to a particular class or data type or instance of that type object. So the terminology of object-oriented languages is I have a template for a family of things. That template might be the strings, or it might be the lists, or the tuples, or the ranges, or whatever you have. That's called the class. And then I have a particular list, 1, 3, 17. That is an instance of the list class. And every object that is an instance of the list class inherits all of the methods that come with the list class. So we'll see a little bit of this as we go on in this class, but not a whole lot. We just do the minimum amount of object-oriented stuff here. And at the last few weeks, we'll actually implement something in an object-oriented way. If you go on in the curriculum, CS 2820 is all about doing things in a language that's predominantly object-oriented. Okay, so what about this dot notation? Well, we've seen dot notation for methods, but we've seen that before. We've seen it when we imported a function from a module. Remember when we imported square root a few weeks ago or a week ago? We were doing the quadratic formula. We had a library or a module called math, and we imported the square root function from that library, and we referred to it as math.square root. And now I have a new thing where I have something like list.index. The notations look the same, but these are different mechanisms, all right? When that happens, when the notation implies one thing for one set of objects and another thing for another set of objects, we say that that notation is overloaded. It has more than one meaning. And you see this in Python a lot. Who can give me an example of an overloaded symbol in Python that you've all used? Anybody? Oh, sorry, go ahead. Absolutely. The plus sign is concatenation for strings and sequences, but it's addition for numbers. Same symbol, it evokes one and the other, but those are two different operations that depend on what the operands are. So the plus sign is overloaded. So for methods, so we have these two versions of dot types, like math.square root. For the with methods, the dot is actually following an instance of that data type. And that instance might be an explicit instance, like square bracket 1, 3, 17, square bracket dot index, parentheses 17. That's fine. Or if I have a variable called x that has that list value, I can say x.index 17. But for functions from modules, that first part, what precedes the dot, is always a module name, a library name. So you can distinguish these two if you need to. Otherwise, if you can live with that sort of ambiguity in your mind, you think, okay, modules and functions get a dot, and objects and methods get a dot, but I don't have a problem with that having two meanings. I think you'll find that the latter interpretation gets easier as you get better at this. Now, the whole point of having an object-oriented language with methods is that you define the method and associate it with the things it's going to manipulate. Right? So in an imperative world where we're writing C or imperative Python, I have these functions over here. They take arguments, and the functions are defined to do stuff. I hand it whatever arguments I want, and the function either does what it's supposed to do with those arguments or throws an error or does something. But the definition of the function is completely separate from the data on which it's going to operate. The data on which it operates only comes to me when I invoke the function. Do I provide the data? In the object-oriented world, the method is associated with that class, list, strings, ranges, whatever. It's associated with the class, and that method is only operating on objects of that class. So if I have a method like index that is defined for strings, I can use it with strings, but I can't use it for integers. If I have a function named index that works for strings, I can invoke it with a string, but I can also invoke it with an integer, in which case it will probably break, but there's nothing keeping me from doing that. And here I'm restricted with how I can use it. Only for a certain data type can I invoke this method. Does that help a little bit? I think if you see examples, this becomes a little bit more obvious. So let's just try some. So list objects have a lot of methods associated with them. You've read about them already if you read the chapters that were assigned, and you know that you've seen these. You may even have used some of these. So here's a list of them. There are actually many more, but this gives us an idea of where to start. So assuming L and L2 are both lists, I is an integer and X is some other arbitrary value, I have the append method, which is attached to a list. So if I have a list and I invoke the append method with X, this, whatever X is, will be added as an extra item, and the list will be one longer. So it gets appended to the list, just like it says. If I extend the list with another list, then all of the elements of L2 will be appended in turn to the rest of the list. It's going to make the list, however long L2 is, the list L is going to be that many elements longer. Oops, sorry. I have an insert element that takes, at position I, it inserts an element X. So it's like you put a new element in and displace everything else behind it down one. Remove X says, hey, if I've got this object in the list, if there's a X in that list, whatever X's value is, get rid of it, splice it out. If that value is not in the list, I'm going to return an error. Notice that if this object occurs twice in the list, only the first occurrence will be removed. We have pop and clear. Clear flushes the list. Pop removes that element in the list. It's like removed, but it also returns its value. So pop is something that has both a value it returns and a side effect. So if I have a list of 20 items and I pop the fourth one, my list now has 19 items, and the value of the pop is whatever the value of the object that was removed is. So I get to get rid of an object and hand it to you. Simple things like count, how many times does X occur in the list? Sort is a destructive method. It modifies the list, remember lists are mutable, and sorts it in that list. So if I have the list 375, I will get back the list 357. In other words, the list will change. It'll be changed, mutated. Reverse is the same as using the index slicing ::(-1). It will take the list and reverse it. The only difference is that here, the reversal occurs in place. In other words, it modifies L, whereas your other reversal does not modify L. It just returns a new L. So this is a critical difference. We've played with mutating L with indexing operations, but we haven't really always distinguished between returning a new list and modifying the list and changing it. We did that in one of the questions of the day, and it was pretty explicit. But this is the way you reverse the list in place. This is the way you sort the list in place. And when I say in place, think of the list you're operating on as a series of bins where every object is in its bin. That framework doesn't change. It's just the items inside have been, messed around. They've changed bins. When I return a copy of a list that's reversed, the original list is still the way it was, and now I have another set of bins that have the same things in different order. And those are two different things. We'll see in practice how that can be useful. So let's just see some examples. So I'm going to assign L to be the list, the range from 0 to 6. What does range 0 to 6 look like? Anybody? How many elements? 6 elements. What are they? 0, 1, 2, 3, 4, 5. And it's a range, so it's a range object. But I'm going to cast it to list, so I'm going to have a new list object, create a list object. It's got 6 bins occupied by integers 0, 1, 2, 3, 4, 5. The assignment returns none, so there's nothing printed at the REPL. The length of L is 6. This is a function. on L. There is, of course, by the way, many times when you have functions on objects like this, that function does nothing other than invoke a method for that object type. And that's what len does. Length is like a dispatching function that takes the thing, you pass it and say, hey, that's a list. Let's call L.length. Or if it's, if it's a range, let's call range.length or whatever. So it often just maps onto specific methods. Sum of L you've all seen. We'll add those together. L.count0, this method looks for zeros in the list and returns how many times it finds it. There's one of them. L.extend, I have another range here from -1 to -5 by -1, so -1, -2, -3, -4, 4-element list. I cast it to a list, and I'm going to extend L by that list. Notice how this extend doesn't return anything. That may be a hint that extend is itself a mutating method, a destructive method. It changes L. So if I now type L, I get back an augmented L that no longer has 6 elements, but now has 10 elements, where this list has extended the original list. Notice, this is not a U list. L has changed. So the fact that I can change, I can do surgery on my list matters. That, by the way, is the only real useful difference between a tuple and a list. Lists and tuples would have no reason to both exist if not for this difference. Sum of L now is 5. The minimum of L is now -4, and you sort of get the picture. Now what happens with an append? Well, like before, like with extend, notice that the value this evaluation of this method returns is none. There is no returned value. So that's a hint that append, like extend, like reverse, and like sort, is a destructive, mutating method. And if we see that, I can extend again, and now I look at L, and I'm going to first have added the -5 that I have here. That was the append. And then the range from -6 to -8 by -1 is -6 and -7, and there they are. Insert 5, 100. Whoop, there's that no value again. Again, a destructive thing. And if I remove -5, well, nothing else returns, so also destructive. Now if I look at L, I'll find that in location 0, 1, 2, 3, 4, 5, I have a 100. Notice how 5, which was in location 5, is now in location 6. It displaced everything down by 1. And if I remove -5, I scanned the list looking for a -5, and there it was right after the -4. And, well, it's gone now. First instance only. If I want to know where -3 is, it tells me it's in location 9. If I do a little fancy indexing, I say, okay, give me the list up to, but not including the index of -3. I get back the 0, 1, 2, 3, 4, 5, 6, 7, 8, but not the 9th element. All very normal. But notice that this slicing and indexing operation does not change the list. There is no assignment here. The only way the list will change with indexing and slicing is if you assign to it. So as it is, L hasn't changed at all. These two things are the same. And L is still my entire extended list with the modifications, the missing -5 and the 100. So you sort of get the hang of this. Go back to that list chapter that you were assigned. Make a note of the different methods. Look at your cheat sheet from the exam, which has a bunch of the more useful list methods given, sort being one of them. Again, notice that it doesn't return anything, but this time, when I look at L, look at that, it's nicely sorted in order. All the elements are there, but from smallest to largest. By the way, in all of these methods, there are optional arguments which I have not provided that can modify how they work. So one thing I might want to do is reverse that list so it's sorted from largest to smallest. So I would go to the Python docs, I would look up the method sort on lists, I would look at the optional arguments, and I would configure the arguments in the appropriate way to sort that list. Now when I reverse the list, again it's in place. They're the same. If I make a copy of a list, so there's a method called copy which makes what's called a shallow copy of the list. So this is important and sometimes confusing. I have a list which I've described before as a series of bins with things in it. Those things are just sitting in those bins. When I make a copy, what I'm actually doing is I'm making a fresh set of bins, but I'm taking the things that I have here and I'm putting those same things in the bins below. Now, if those things are numbers, say integers, if I modify the second list, it doesn't affect the first list. I'm just changing the number 5 to the number 17. All good. Now the second list deviates from the first list. One has a 5, one has a 17 in that same bin position. However, if the objects in that bin are themselves lists, and I modify the object in the first set of bins, that modification is carried through to the other set of bins as well. So we're going to see that, I think, in a second. So here I can sort. I have L2 as a copy of L. I've sorted L2, so I'm back to having it in order. But notice that that doesn't change L, which is still sorted in the reversed order. Each one of these bins, when I made the copy, all of these elements were copied into L2. When I sorted them, they were rearranged within the bins of L2, but the elements themselves haven't changed. This is the same element, 100, as this 100. For the integers are always the same. What happens when I pop? Well, pop by default removes the last element of that list. And at the same time, so I've popped set -7. I pop again, that gets rid of the -6. I remove the 100, that's the first element. Now when I look at L, the 100 is gone, and I've eaten away the last 2 elements of the list. You all sort of getting the hang of this? I mean, it's not hard, right? There's just this family of methods that you can use to play with the list. And that you'll be doing this actually a lot. Notice that while this L has been destructively changed or modified, L2 is still what it was. It still has the full complement of elements. So we've done something like this when we do indexing assignments. So we've seen, for example, taking the second element of a list and assigning a U value to it destructively changes L. It basically refills the bin with this new thing. We can do that with the replace. We can replace an element in the bin. We could remove that element and insert a new one. There's all sorts of things we could do to achieve the same purpose. Sometimes it's much more natural to think of using slices and indexing assignments because it's sort of the natural way to think about this. Other times, you might want to have that series of appends and extends and splices and removes and whatever it takes. So choose your technique wisely. This is an insertion of these elements inside the list. Notice that there's no easy way to do this with the list methods. There's an easy way to append at the end of the list. It's not an obvious way to appending in the middle of a list. It's just not obviously done. Here, I'm basically taking this 6 and I'm adding it at the end of the list. So this is essentially the equivalent to an append. The notation is different, but the effect is the same. Here I'm going to do, this is in fact an append in operation. There's no easy way to do, this is really an extend because I'm giving it a list. Whereas an append would just have the 6 added here. But, appending one element and extending by a list of length 1 are sort of the same thing. But you can see that the same technique here actually can be used to append more than one element at the same time, and I get all 3 of them. Okay, well, guess what? Strings have methods too. They have a lot of methods. You've seen a few. Many of those methods are the same as the methods on lists. Not identical, but the same. So for example, indexing is kind of the same. The difference here is that in indexing for lists, the thing you're looking for is an element of that list. An element has to be in the bin. Whereas because strings have this funny property where an element of a string is always itself a string, here I can index subsequences of the string. Does everybody see the difference? In a list, 1, 2, 3, 4, 5, I can ask, where is the 3? I can't ask, where is the list that looks like 3, 4? Can't do that. Doesn't work. But with a string, the element in the bin is itself a string, and strings allow us to extend some of these methods to subsequences of the string itself. So the index, while the method name is the same, and the operation is largely the same, it has different capabilities by virtue of being implemented on a different type of object. Some of these things, these are Booleans that return true or false. Some of these things just check, is the string all digits, 0, 1, 2, 3, 4, 5, 6, and so on? Is the string all alphabets? Is the string digits or alphabets? Is the string just all spaces? Is the string in uppercase? So all of these are specific to strings. You don't have anything like that for lists. Nor would you. Doesn't make sense. We've seen join, which takes a sequence of strings, either a list or a tuple or whatever, and replaces and joins them together, returning a new string based on having that paste character specified by this S, or that paste subsequence. And you can sort of see the same kind of thing. We have a replace. Oh, but here replacement allows us to specify how many copies I want to replace. That's useful. I have a special thing that does a strip. It says, take the string, and by default, if there are any white spaces at the beginning or end, remove them, trim the string back. We've seen upper and title and lower and so on. Now, one thing you have to recognize about strings, what was the first rule of CS1? Lists are mutable, strings and tuples are immutable. All of these methods do not destructively alter S. So when I replace something, where is it? When I replace something in S, unlike with the list method by the same name, which makes changes to the list, I can't do that here. Strings are immutable. So the net effect is that I'm going to return a new string with the operation done on the new string. Keep that in mind. You're dealing with lists and strings are going to be different. There are methods for tuples and ranges. Every sequence type we've seen, there are certainly methods for dictionaries. There are methods for sets. Sometimes these methods will have direct mappings onto operations you already know. For example, set intersection is a method. S dot intersection, and then you pass the other set. But we know set intersection also has an operator form. So there are multiple ways to access the same functionality. Use the operator form when it's more natural. Use the method form when it's more natural. All right. Oh, this is great. We have 14 minutes. My favorite part of the class. Everybody hates this. I think they're fabulous. So this is going to be a wild ride, so wake up because we can do a lot of these, and this is going to be fun. Try to look excited. I'm 65 years old. Make my day. Look excited for comprehensions. So Python lets you define lists on the fly. We've already seen how to define a list. You just put square brackets and put your stuff in it. And I know a lot of you are just dying to use for and while. We're not going to use for and while for a while yet. But we are going to learn about this form called a comprehension, which is an iterative form that lets us create structure. So its only purpose is to build new lists. The general form of comprehension looks like this. This is called a list comprehension. There's a square bracket and a square bracket, which tells you right away, should tell you, oh, list, I'm making a list. But instead of having comma-separated values that make up that list, I have something to evaluate that says, evaluate this expression for every x in the sequence type. So you can think of this There are idioms in programming. And there's an accumulation idiom where you take a thing and you do it repeatedly and you collect the results. This is an example of that idiom. So let's take a look at an example. I can do list comprehensions over any of the sequence types or over sets or dictionaries, however you like. The more general form of sequences looks like this, of comprehensions. I have any expression with, some number of variables. For X in one sequence, for Y in another sequence, and then there's a bunch of filtering conditions. So this is the full form of a comprehension. We won't start with that. We'll start with the simple ones, which are 90% of what you use them for. So here's an example. Oh, I started with the complicated one. Sorry. So here's a full one. I have a list comprehension indicated by the square brackets. This is a tuple of X and Y. I don't know what X and Y are, by the way, but it's a tuple of X and Y. And then I see these two subparts here. The first one says X is in range 3. Well, range 3 is 0, 1, and 2. So I'm going to see that this thing means I'm going to allow X to take on each value 0, 1, and 2 in turn. So first X is 0, then it's 1, then it's 2. For each one of those values of X, I'm going to let Y take on the values 0, 1, and 2 as well. So this subset here lets me think of collecting all X and Y's where X is 0, 1, 2 and Y is 0, 1, 2. So 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. All of those collected as tuples will be the result of this list. Oh, but wait, there's more. There's a filtering condition that says only if X and Y are different. So scratch 0, 0, 1, 1, and 2, 2 because those are filtered out. And the result here is a list, as promised, because it's a list comprehension. List comprehensions always return lists. And the content of that list looks like this thing collected over the ranges of X and Y when X and Y are not equal. And in fact, you'll never find a pair here where they're equal. And you can clearly see X is 0, Y is 1, Y is 2, X is 1, Y is 0 and 2, X is 2, Y is 0 and 1. How cool is that? Right? It's pretty cool. All one line, one little piece of code. And you've done this. I guarantee you, those of you who love for loops, you can't do this in one line of code. It just can't be done. This is a simple, concise, explicit description. Build me a list that looks like this. I can refine this. I can give a different filtering condition. And now I will not get the duplicates in the unordered sense. In other words, I have 2, 0 and 0, 2. Here the first element will always be greater than the second. So it's an incredibly powerful mechanism. Any math majors? Yeah, so in math major, when you write in a proof, you have a little curly bracket and you say X such that X is this. Common thing in math. I don't know which math class. We do this all the time. This comprehension is inspired by exactly that notation. So in math, when you write X such that thing, this is saying expression XY such that X is in this, Y is in this, and condition is met. It's exactly the same thing. This seems awkward to people who have written in other languages, but if you think of it from not a programmatic, algorithmic point of view, but from a declarative point of view, what does that mean? It means I'm not going to tell you how to compute this. I'm going to tell you what I want to compute. And let Python do it. This is a perfect declarative statement. Give me a list that looks like this. There it is. I don't know what happened here. Oh, yes. There are always many ways to skin a cat. You'll notice that this filtering condition can also be fulfilled by saying let X range from 0, 1, 2, 3, but let Y only range up to but not including X. So even without the filtering condition in this explicit comprehension, I never generate a Y that's equal to or greater than X. I just don't do it. So I don't need to filter it because I get the same result. It takes a little bit of practice to figure out how to use comprehensions. You'll be getting a lot of this practice, not on today's question of the day, but starting next week, they'll all be comprehension kinds of things. Now, we've seen list comprehensions, but guess what? We have set comprehensions, we have dictionary comprehensions, we have a bunch of different types of comprehensions. So here is a set comprehension. Again, the curly brackets rather than the square brackets says I'm a set. And here I have x plus y for x in range this and that, and I get back the set with those values in it. Very natural. Oh, this also looks like a set, but in fact it's not. It's a dictionary. Why? Because the element I'm collecting here has the x colon y form, which is key colon value. So I told you before, sets were special cases of dictionaries where there's no values, just keys. The keys of a dictionary are themselves a set. That's why true and one, only one of them stays the same. These are intimately related. They both share the curly bracket notation. But here, the special dots, the two dots, indicate that this is collecting key dot value. And so this is actually a dictionary. And I get back a dictionary. Is this sort of starting to make sense? List comprehensions, set comprehensions, dictionary comprehensions, they all kind of look the same. I can do the same kind of thing I did before, where I have a range and another range and a filtering condition. All that stuff works. In this case, x is range 3, 0, 1, 2, 3. And then I have, oh yeah, so here for every x, there's 0, 1, 2. So there's only 3 x's. I'm going to have a bunch of y's. Right? I'm going to have two. I'm going to have 2, 1, and 0. So y goes 2, 1, 0 by minus 1. And notice that the value here is 0. Why? Because the last one added takes precedence. The only reason that this is a 1 here is because x is 0 and I don't allow y to be the same. So because the keys of a dictionary are set, duplicates are not allowed, you may not get back everything you think you're going to get back from a dictionary comprehension. If the keys show up more than once, the last one added takes precedence. So this is a common beginner error. The intention is to make a dictionary comprehension, and you do it like this. That's not a dictionary comprehension. That's still a set comprehension, except it's a set of tuples. It's not what you want. The colon matters. That's what makes it a dictionary comprehension. So why not string comprehensions? Now, I can use strings as the target sequence I'm iterating over in a comprehension. I can do that. But there is no string. I can't write in double quotes x for x in whatever. That doesn't work for strings. So here's an example of a list comprehension where the sequence I'm iterating over is a string. So x will be t, then e, then s, then t. And I'm going to collect the uppercase version of that, which gives me a list of uppercase letters. I can do that. But I cannot construct a string as a comprehension. However, there's this fancy string method, which you've already seen, that takes a sequence of string elements, substrings or characters, and converts it into a string. Anybody remember the method? How do I take a sequence of elements that are characters or strings? Go ahead. Join. I use the join method. We've seen it before. There it is. Here's my comprehension in the join. I'm going to splice those guys together with the empty string. That's the paste or glue that holds each of these elements, which you see here, together. And I get back the uppercase string testing. Okay? Now, this is stupid because I could have just taken the lowercase testing and said dot upper and I would have gotten there right away. But you can get the gist of how this works. Maybe I would like to remove all the t's. So I could alter this and say for x in testing, if x not equal to t, and then I would have got s-ing, all caps. So be careful. Here's a join with some fancy paste or glue, 3-character sequence. And this is a set comprehension. But sets, remember, the order is not guaranteed. So when I paste this together, I might not get these back 0, 1, 2, 3, 4 because the set may not have these in order. That is implementation dependent. All right? So remember, all of these sequences have their special characteristics. Strings are immutable. Tuples are immutable. Sets are order independent. All these things have implications when you use them in comprehensions. What about a tuple comprehension? We have sets, we have dictionaries, we have lists. We don't have strings. Do we have tuples? And the natural question. The answer is no. But what we get back is really interesting. We get, instead of a tuple comprehension, we get a generator expression. So what is a generator? So let's just think about a list comprehension where I'm collecting x for every x in range from 1 to 1,000,000. What will I get back? Get back a 1,000,000 element list. Starts at 1, 2, 3, 4, 5, all the way up to 1,000,000. Actually to 999,999. Okay? A 1,000,000 element list. So let's say you're doing your homework in lab and you type that expression in, and all of a sudden you notice the machine starts scrolling to print out 1,000,000 elements. And it's scrolling, the machine's not very fast. You can be there all day. If 1,000,000 isn't enough to keep you there all day, 100 million guaranteed, right? 1,000,000,000 guaranteed. Yet the description of that comprehension is very brief, right? Because it's still collect x for x in range 0 to 10 billion. Yet the incarnation of that comprehension is this giant thing you don't really want to see. And in particular, you spend some time generating that list and creating it. That's computational time. It matters when there's 1,000,000,000 elements. So what a tuple expression, a tuple comprehension, which isn't really a tuple comprehension, creates is this object called a generator. And the cool thing about the generator object, it's a lot like a range. It's an implicit representation of something. A range is an implicit representation of a long collection, a long sequence. The generator itself is exactly an explicit representation of a sequence that we have not yet generated. And it carries with it all of the same sorts of things. If I wanted to add together, and so this inner set of parentheses creates a generator, I can use a method like a function like sum on all of the elements in a generator, and it will actually generate all those elements and add them together. But if I want to just know what the 47,000th element of this generator is, I don't need to create the whole list. I just can go in and pluck out the one element I have. Now, we're not going to spend a lot of time on generators. We will use them later in the term. But I just bring them up here because you should know there is no such thing as a tuple comprehension. If you try to make one, you're going to get this puzzling object. So we've learned today about list comprehensions, set comprehensions, dictionary comprehensions. We're going to be comprehending a lot for the next week or two. So see you on Monday. Have a good weekend. There will be a reading assigned. I haven't done it yet, but I'll assign a reading for Monday. Thank you.